Hey, it started. Okay. Well, good afternoon, everybody. So I just made an interesting discovery when I logged in. If you notice, like the last video that we had just was not uploaded, or it's not available if you check. Because at the end of the class, it had shut down and I couldn't recover it. And it looks like when I just logged in right now, it all of a sudden found it. So we might actually get back the last lecture. We'll see. But it found something from when it crashed. So who knows what we'll get. Today we're going to go over MRI technology stuff. So the idea last time was really to cover the physics. There'll be a little bit of an overlap because it's kind of necessary for the physics and the technology to overlap. We're trying to talk here about how do we actually do it, to implement the ideas behind there. So that's kind of the flow of this. So this is roughly the second MRI chapter of the book. I think it's, I don't remember the number. Maybe it's 13, I don't know. Whatever. I think it's 12 and 13 are the two MRI chapters. Anyway, I've included, so that's woohoo, look, here's an MRI machine. They are a little bit bigger. So the way you can kind of, if you're like looking at an MRI versus a CT scanner, CT scanners are smaller. That's probably your biggest single indicator that's out there. It gets harder to tell just by looking the difference between an MRI machine and a PET or SPECT machine. Well, SPECT you usually have the anchor cameras. But on a PET, it's kind of a circular one. It can look fairly similar shape-wise between them. Other than usually you'll have like a gigantic empty space around it. Kind of shows these close to each other, but they're nowhere near each other because that magnetic field will suck anything in. So MRIs you can usually also tell just by the room they're in. They usually have a big empty space around them. With lots of calming, like soft pictures on the wall, just to get people sedated. They can be quite deep tubes. There are a few different types that are out there. Really the difference between these two, it's kind of hard to see in the picture. I just grabbed it off the internet to give you a sense of them. There are what they call these wide bore versus the narrow bore. Wide bore is really meant to make you feel less cramped when it's in there. The narrower the bore, the closer the RF coils are to you, the better the image is. To enhance some of that, they'll sometimes put coils right on the body or around it, so there's like head coils that can snap in and integrate to be able to take those measurements. Anyway, that's those two main types. Then there's what's called the open MRI. It's kind of taking the whole thing and twisting it 90 degrees. So you're kind of coming into a slice in between the two. Yeah, it's for people who are freaked out, it's much more open because it's kind of, it's like two pillars with donuts top and bottom, so to speak. It's not going to be as good, I'll be honest. You'll still get a good image, but it's not as good as you would get on a regular machine. But for some people, particularly if you have a longer acquisition time, it's going to be a more survivable situation, I guess. The other thing I grabbed this one off the internet too, because I find a lot of people have no sense of what generally these things mean. So there's two basic units we use for magnetic field. Anybody remember the two? Gauss and Tesla, yeah. So 1,000 Gauss, 1 Tesla. And why exactly we blew two awesome, scientists and mathematicians from the past for one particular thing where they're really just a trade-off like that. I honestly don't know. So the Earth's magnetic field is a nice kind of reference in my book, right? So that's roughly somewhere around 50 microtesla or 50 You know, that's kind of, if you ever pull up your phone, it'll often have a measurement one. It's usually accurate to a Gauss or so, most phones, being able to measure that. That's kind of how they find magnetic north and everything too. So you certainly don't want your system in here. So, but if you think of this as 50 microtesla, so a really, really tiny, sorry, it's like half a Gauss, I should say. You're dealing with a really, really tiny value. Typical things like a fridge magnet that you put up are around 50 Gauss. If you get one, this is kind of a fun one. You ever see those junkyard, pick them up? Right? That's 1 Tesla. That's a pretty strong magnet. To think our clinical scanners, it says 0.5. I'm going to say 0.25 because the particular MRI you're going to use over in physics is 0.25. So it's designed to be a small one. Now, it's no longer in regular clinical use. I think there's a few of them in clinical use, but it's pretty small. But 3 Tesla that it puts as the upper end, I mean, if you take that as a typical range and you allow some outliers, then sure. You know, research MRIs 7 to 11.7. It's getting up above 11.7, so the latest ones are bigger than that. But you know, anyway, the ones I found fun were the last 2, just because I didn't know these numbers, but I thought it was just kind of neat when I found them on the chart. The largest magnetic pulse field created in the lab without destroying things was 97 Tesla. And the largest one ever created, which destroyed the lab, you know, or the equipment and everything. But it's kind of neat that they know, but not the lab itself. 730 Tesla. That is just, yeah, that's an insane field. And if you think about the fact that it kind of destroyed the equipment in creating it, it's kind of neat, but it gives you a scope of just how destructive it is, you know. So I guess Magneto is somewhere down in that 730 range. Sorry, I like Magneto, so.
It's cool.
He is a cool character. He's cool because he's not pure star. He actually, you can't really call him a villain. You can't really call him a hero. Right? He's whatever he is at the time. And you kind of sympathize with anybody who went through the Holocaust, right? It's kind of, you know, from the original storyline stuff, that's what got him all messed up. Right? So, all right. So MRIs, how are they generated? So if you notice, we've got the RF coils on the innermost area. That's kind of the really important area because you need that RF coil as close to you as possible. We also want the main magnet as far out as possible because that's going to create an even field. And the more even that field is, the easier it's going to be able to read things off accurately. Because any deviations in it's going to look like, you know, a deviation in the gradients, which are important to us. This doesn't actually show all of them. There are also little shim magnets that we put in that allow us to adjust to try to linearize this. So tuning in the morning, there are these little shim magnets that go into there. It's not part of the regular running, right? Well, they're on in the regular running, but they're set at whatever it had been in the morning. So you kind of just use them to get the field to go right for it. It doesn't show here, but there's actually lasers that are set up within the room as well to do the alignments. You need the lasers because you have to align, and B, you don't want anything in the range of it. So, but you can see there are X, Y, and Z ones. I tried to give you a couple of these ones that gave some general ideas, right? So the outside one is like really big coil, single wire that's wrapped all the way down. It's usually pretty stupid thick. And that's the one we really care about when we're liquid cooling. Yeah, because you need that field, the main field, to be crazy stable and linear. Because all the other stuff you're going to be adjusting how much you want it, the gradients on it, to be able to create an effect. But that main magnet, you need a very constant and as pulses and everything are going on. You don't want it heaving, you don't want it shifting, anything else. That is your North Star, so to speak. So it's got to be very, very well set. And then there's images of the gradient coils that are on. We'll take a look at them in a little more detail in a second. And then there's going to actually be a bunch of different coil styles that are going to be in, and we'll take a look. This is a bird cage style that's shown here, but yeah, we'll take a look at a few different ones. And yeah, I do suggest reading the book. I'm not going through as many of the equations in here, but I'm going also through some stuff the book doesn't. So I'm going to try to mention differences between how you set up the transmit and receive, whether you do it on one coil, multiple coils, things of that sort. Yeah. So most of the people doing this, they kind of consider the main magnet and the gradient as the magnetic field. And they consider the RF not the magnetic field. And this kind of gets to the question you had asked last time when the book says it's not magnetic field. And I hemmed and hawed about it. And it's because nomenclature-wise, we would not call it magnetic field. Reality, we know anytime you get a light pulse, it's an EM pulse. But it's not considered as part of that, even though it is an EM. I guess, yeah. It's one of those things where you play a fine game. It kind of kills me in one sense, because if you were to look at it straight, just according to basic physics, it is trivially EM. Yeah, but when you're looking, and when we get down to breaking down the other stuff out, it's nice to be able to consider it as different, because we're gonna, for the simplicity of the analysis, it's easier to consider everything else as the EM field, and RF is just our kicker. So, yeah. Anyway. Boop, boop, boop. All right, so let's deal with the big bad boy first. All right, so this is kind of the books area. So typically you'll see there's an outer area that has liquid nitrogen on a really big fancy machine. For ours, we don't usually, I think he only uses liquid nitrogen, but he might just be liquid helium. I'll have to ask him again which one it does. But in essence, what he's got is, or a typical one, we use liquid nitrogen on the outer two areas, kind of almost as like an insulation layer of them. The inner one right around where you have the first and the second niobium titanium wire, which creates the field, is usually in liquid helium. And then in a sense, it's kind of like a, one of those really nice mugs that you get that have, it's metal, but then you have a gap in between it. If you have a vacuum or certain noble gases, usually in this case, we want all the way to a vacuum. They still air or a vacuum is a really good insulator, actually. We tend to think of air as a lousy insulator, but it's actually not if it's not moving. Right? And again, if you've got a vacuum, it's the ultimate still, because there's nothing to carry it. So you lose both conduction and convection as methods for carrying it in a vacuum, and you only have radiation between them. And it's at a very low temperature, which means black body radiation is really stinking low. So therefore, you're not going to get a lot of losses in that sense. So that just makes it really efficient. So they're trying to show you there that there's vacuums between the liquid helium and the liquid nitrogen, and between the liquid nitrogen and the outside all around. The lower ones, I thought their picture was kind of ugly, so I found this one that was 3D on the internet that I think just gives a better sense of it. And also shows that on the inside of this is where the gradient coils and everything else goes. So this is kind of fitting around them. And then there was the lower slice cutaway here. Did a nice job of kind of showing them separating the layers. Right? So we've got the magnet, the gradient magnets, and the coils, right? Coils are RF coils. If you ever see the word coil, you know it's only dealing with those, even though everything is coil. Like this is another one of those kind of more nomenclature issue than, you know, a physical reality, but, you know, these magnets are actually coils, as are those ones, right? But this is the one called the coils. Patient positioner, truly this rotates around, and that's what they're trying to show there. The patient positioner doesn't cut into it, they really go all the way out. So, and the important thing from this one is that Z is pointing towards the feet when you're looking at those. All right. Now we go to stage 2 of our magnets, right? So we're going to have 3 different coil magnets. I thought theirs was ugly. I found a nicer looking one that was kind of 3D, and I like the color coding. Plus, it used green and yellow, and that was pretty irresistible failure. So the Z ones, let me start actually on here. Right? You can see the Z coils, those 2 locations. It's kind of nicely shown out here on the green. You know, this one is pretty much useless by my mind. But you can see the Z coils, which is going to set up basically this ramp function down your body. And that's these gradient coils, the whole purpose. Well, let me ask you, what do you think all these gradient coils are used for?
The strength of the magnetic field determines the starts with L.
Yes, the Lamore frequency, which is how fast it spins. And that's how we're going to do spatial encoding. Right? Because we can now create these ramps, we can cause things to rotate at different speeds depending on where they are physically. Then when you do a Fourier transform, you're going to resolve out all those physical things. So we're actually going to measure all of them in a range, and then we separate the frequencies out, and boom, you're done. Right? So these are kind of essential for that area. This is all spatial encoding. So if you want to put into a 2-word thing, why have gradients? Spatial encoding. This is basically essential to generating the image itself, resolving individuals. So then we just need coils for Y and X. You'll notice those 2 look fairly similar. They're just spatially located on there. And that's going to do what's called Y is the phase and X is what's called readout. You know, sometimes called frequency encoding on them. So that, but that's what those 2 ones are going to do. They're definitely coupled. We'll see a couple places where we move Y and X simultaneously, because essentially by the Z coils are just going to select where you are spatially top to bottom, so it selects a slice. And then the X and the Y are going to allow you to scan basically on how you move through them. And we'll look at the pulse sequences to do that, but that's really going to be the key. We'll set these to find out where within the body a slice, and then by setting appropriately patterns of these, we'll actually move through the space to do readouts. These are usually set in combination with also the RF coil, because for instance, you got to keep these constant when you're giving those initial kicks, right? Otherwise, you're going to cause some problems. It's got to be constant during readout. It's another key aspect of them. The 180-degree kicks when we flip or invert stuff is going to flip or invert whatever we're doing here too. So we got to take that into account also when we're reading them out. That'll become important when you're seeing the pulses. Yeah.
So are you saying like basically the different orientations of the gradient coils determine which plane you're imaging?
Yeah, how strong you set those.
Okay.
So you're going to take a look at it, right? So I've got the ability to set those coils by adjusting how much current I'm flowing through them. And that will set how big that slope is, which will differentiate the field. And the key trick is going to be, like for instance, on selecting a slice, I'll set my Z coil to a certain amount, and I'll pick my kicking frequency, right? The RF coil. I'm just going to call it kicking, just so you kind of think of those terms. if it is the same or when it's the same frequency as a particular spot in your body, caused by the Lamore frequency of that gradient, when they're the same, you'll get a resonance peak. Boom, that's where you're gonna, everything will move there. The other ones are not resonant and they'll just die off. Right? So, you know, in essence, it allows you, by setting these, you can just kick a single slice, and that is the only slice doing anything. Right? And so basically you have to set, however the RF coil is causing the disturbance, the kick, and we have to set it to be the same as spatially what the rotation or the natural frequency is going to be set by the Lamore frequency. And that's really the trick to it. All right, so we do that Z1 into with the initial RF pulse. That sets one slice rotating. And then we kind of screw with it to adjust which ones within there we want to do. Y will deal with phase depolarization, and X basically deals with slightly adjusting the frequency to get a readout down the line. But that's essentially how those fly.
So we talked earlier about how the VDOT field is, we can in the middle assume that they're perfectly straight, and at the end that at the ends they are, it kind of doesn't work out super well. So for the gradient coils, is there a similar type thing where we're assuming like a planar gradient and it's not actually, is that something that's strong enough that needs to be corrected, or is it generally just?
It's usually fairly close.
Okay.
There's always, I have to hem and haw a little, right? There's always going to be some variation that's within there. And we try to adjust them. That's what, I mean, it's not mentioned here, and it's a little bit deeper than they want to go in the book, but I think it's a good question. That's where all these shim magnets and everything else comes from. Trying to adjust it within to make sure it's not going to be perfect, but that it's good enough.
I see.
So you'll take that, a few millimeters to whatever, depends on your system and what resolution you're looking at. Since the table can move, we'll often only image when you're far enough into the tube that you're not getting the edge effects. So again, you kind of want it between those two Z gradient coils. That's going to be your flattest uniform field, because you'll set one stronger, one weaker, and you'll get a gradient right between them.
Yeah.
And as you drop off from that, they're still down the tube, which will straighten it a little bit, because the effect of the other coils, there are some induced induction that's coming on these, and so therefore you will get a little bit of that kind of flattening of the field, but it gets uglier and uglier the further out you go. So in general, you try to stay inside that kind of sweet zone. And they actually locate these, it's called the isocenter, where they find the exact middle of it, and then there'll be an imaging volume inside, where it is considered good enough to get a high resolution one, or correctable by fusing with an X-ray. But even with the X-ray fusing, you have to do it with a nonlinear. You kind of consider everything a fluid, and you nonlinear map it. Anyway, so this, again, it's not in the book, but I thought this gave a better picture of what's going on. I've been trying to find animations for these, but what I've discovered is most animations are covered by copyright protections of companies that want to make money off animations for these. At some point, I might actually persuade my daughter to see if she'd be willing to generate something, because my middle daughter is an art person in that, but this is kind of boring stuff to her. So at the moment, this was the best stuff I could find that I could use. Like most of these are scrapped out of people's articles and stuff. So I try to give credit where I know where it came from, so I can call it fair use. But anyway, the top one I actually really like, right? So you've got, imagine you had a fixed one, right? You get a base frequency, and you could say 42.6 or whatever. And then imagine this was a wedge that sat on top of that. Right now, in reality, it's plus or minus from the field, centered on it. But for simplicity, this is good enough. So you can see the base one, and as it goes up, you see the Lamore frequency spinning faster and faster. And so you can imagine if I give an RF pulse that's tuned for 46.6 megahertz, only the one that's at that frequency will respond. The other ones are out of sync with it, and so it's not going to respond to it. So they won't really have any decent amount of kick to them. So that's kind of a nice area. The Z gradient, this is part here is kept constant when you do the initial perturbation to get that going. And then the Y gradient and really the X gradient, both of them, see how they kind of show this? It's trying to say different amplitudes, plus or minus on the field. And that sets what the phase is. And we'll show you how it does it. But it tries to give you a little bit of an idea here that as I'm going up, I'm kind of walking up the phase shift inside, therefore the spatial frequencies, or down, obviously down. Right? It's in the Y direction, so off it goes. A similar thing happens for the Z, or sorry, for the X. This is when you do readout. Right, so you always go down and then up because it takes care of any weird phase shifts and other stuff that might be going on, or typically do. And that the X kicks will let you push down a route. So essentially, when you're looking at this, imagine this is your frequency space that's in. I can then think of how I set that Y gradient and X gradient as basically moving me around the plane. The Y gradient, the phase encoding, once you set it, it'll keep running for a while. Right, so you've perturbed it. And what you're really doing there, it talks about phase encoding. It doesn't really show it as well here. And that might not look like phase to you. But what you're actually doing when it's talking about phase, it is kind of phase in one sense. But in particular, remember we talked about the phasing, dephasing of all the tops, how they're spinning and the net effect of it. That's what you're actually perturbing. And in different areas, you're setting the phase of it. So some of them will dephase faster than others will, which allows you to then read them out, right, based on your output reads. And that's all on the TE, the echoes, and the repeat, the TRs, which we'll get into what those will set for you. But essentially with this phase shift, I can set how fast different regions will phase, dephase, and therefore how fast I can read them out, which will give me a particular height differential, because this is all being done only in the Y direction. And then we change the readout. It's called readout because we do it at readout time, right? And that will just change the Lamore frequency slightly down the X direction. So therefore that frequency differential will then show up in the read. And you're actually reading the whole thing at once. You just need a bunch of samples to get a good measurement of it. Does that kind of make sense in the basic ideas?
I have a question. So
Yeah.
These XYZ gradients, those are actually physically, spatially degraded.
That's the gradient coils.
Okay.
Yeah.
So I have a question about that. So if we have our 3 dimensions XYZ.
Right.
If we give a gradient to each one of them, they don't have to be scaled or something. Wouldn't that just create a plane of constant frequency?
But we don't do it at the same time. This is time.
Oh, I see.
Right? So yeah, no, that's a good question if it doesn't make sense. Yeah, this is time progressing. So we're not doing them at the same time. The really important thing is, right, that is the effect it's going to create, is to adjust every time I do this, it's going to adjust the Lamore frequency. When I do the Z one and I set it head to toe, I'm making head to toe different frequencies. Then while this is at that peak, which is while that gradient is established, right, this is the upswing, right, this is just to correct any shifts and phase things whilst depolarizing, right. I kick it, and I kick it, right, with that RF coil, and I set the RF coil's frequency to be whichever slice I want it to be. Right? So this allows me to set that area. In truth, I might even adjust this up or down because it changes where it is. Because all I care about is how do I set a particular slice to have a natural resonant frequency, and then I kick it with that resonant frequency. All the other ones are ignored. Now it's spinning. Once it's spinning, I don't need that anymore. Right? Think of this as spinning your top in the first place. Right? So I kind of encode this Z field just so I start one slice and one slice only to start spinning. And it's done by a combination of this C gradient and the RF. And that's why I said they work in concert, right? I start the spin variation, hit it with the RF at whatever I want, 47.9 megahertz, for instance. If that's what the frequency I induce from the RF coil, only that one near 47.9 is going to be spinning. The other ones will not get the energy from it, right? They don't resonate. So if you kind of just think of it as a resonance situation, that's the whole trick. If it's not resonant with it, it's not going to vary. And if resonance doesn't make a lot of sense, just think of people marching across the bridge, right? This is kind of the classic situation. If you've gone across a bridge and felt the up-down swing, you're in resonance pulse with it. If you walk out of phase with that, it dies out. Because again, it's just, not being in frequency with it, you're not pumping it always at the same time. Okay? People also use, the wine cups is another classic example. If you get the resonance frequency, guitar strings, you pluck them, you kick them with one thing, but they have an innate resonant frequency. If you were able to pump in a frequency wave that wasn't in tune with the resonance frequency of a guitar string, you wouldn't get that nice note. Right? It would cancel out. Right? Your highs and your lows would cancel, and it's all done with. Whereas if it's resonant, the high will get another high pulse and go higher. Right? So that's what we're doing on the first part. So literally, we do this at time 1, set that pulse. Now it's going, I'm going to quickly kind of kick the phase, right? Because this is now at the point, now that they're spinning, I'm going to want to do something to cause them to dephase. So I can do the measure out. So I'm going to set the dephasing frequency as it's dephasing. That's why I do the Y gradient next.
Okay, so
and then I read it out afterwards. And at this point, once I've set the dephasing frequencies are set. They're going on. Now I'm going to do my echoing or whatever. There are gaps between these. They're just not drawing them. Right? And then later on, when I'm getting ready to read out at the last sec, I want this to correspond with my analog to digital converter, the ABC readout.
Is there a reason why you want the X?
Because we picked it as a convention. You could have flipped these two if you wanted.
Okay. So I have a question. So the Y and X, they move at the same time. Is that so you can pick a phase next by plane?
Yeah.
Weighted? Okay.
Yeah. When you move these together, it's no longer for readout. It's to position yourself in the plane.
Right.
When you're doing it, it's nice, for instance, to move over to the side.
Right.
Now, one way you could do is you could go up and then you could go over. You hit it with a 180 pulse and you're down here. And then you do a readout. And we'll take a look at some of these combos. The last half to 2/3 of my slides, so that's all they are, showing you different pulse sequences. But I want the idea to make sense before we go through, because this is all the magic. The rest of it's just working out. If you understand this idea, you've got it. So what other questions do we have about what these mean, how those encodings work?
So I have just a quick question about how we get to K-space from our kicks.
Yeah.
I guess I'm not following.
Okay, so this is the fun thing. We're actually forcing that to be what's happening
I see.
in reality, right? Because we're going to set the frequency, right, by the slice area. So I've already got a frequency set.
Right.
Then I'm going to set the depolarizing. That is literally setting, and I'm doing it spatially, right? That's on, but it's going to be a phase effect to them. So I can then read the K space, the Fourier space for it, is what I'm going to read out.
Right. So
because they're all superimposed.
Right.
The system is going to superimpose the spatial ones.
Okay, so I think I understand the y-axis of the 2D plot of the K-space.
Awesome.
What does the x-axis represent?
So what the x-axis is going to be your x spatial axis. And what I'm going to do is by setting a gradient in the x direction during readout, and it's small.
I see.
What's going to happen is it'll perturb. You're going to be on, by the way you set the dephasing, And when you set the measurement time, because remember the dephasing, it'll make certain ones dephase faster, some slower. So if you set your readout when the faster ones have died out, right, and the slower ones haven't resonant peaked yet, right, you put that to be where your measurement time is. So basically how you set this dephase will tell you how much time to make before you read this out.
I see.
Right? And so this is going to set them to be in the Y direction, right, back to front. Right? It's going to set them, so some of them are dephasing faster, some slower, and it will be based on the height, or, posterior and anterior direction, right, inside the body. It'll set them to be dephasing at different amounts. Remember, I picked my echo, that little, kick it to cause it to re-resonate and recombine. If I set that echo time so it's peaked for your phasing at a particular level, the faster ones go away, the slower ones haven't peaked, so you just get the one you care about. So now you've picked a Y level by how fast you set the dephasing. So now all you have to do is determine left to right. And so all I do, now I've got only one particular row across my body, right? Because I picked my slice with my Z of who's activating, right? So I have a slice. I picked my dephasing, so there's only one height area. So now I've got a little volume. So now what I'm going to do is at the last sector, I'm going to do a slight Lamore shift again at the readout. And they're going to all superimpose on each other, but they're at different frequencies. So one side will be slightly faster than the other when you're reading it out on frequency, so it separates in the frequency plane. So when you read in that thing, you've got the superimposed frequency. You do an FFT on the initial one that fills up your K space, and you write that K space line in, right? And then you'll do an inverse FFT once you've filled the whole K space. But you're going to do a line-by-line read, and you separate out the left to right, because you're going to, that's why this has to be constant over the whole time you're doing the readout, because you're really just holding the frequencies a little bit out of where they want to be, but so that you get a spatial encoding. So you could go, oh, the slightly faster ones are on the right, the slightly slower ones on the left, and there you go. Does that make more sense? Right? The key idea is the first one just sets who's rotating. The next one sets how fast they dephase, which means when do you read them out. And the last one at the last second just goes, twist them a little bit so I can tell left or right. That's the whole trick. That right there, that's MRI. Right? So we'll take a look at the particulars. I just wanted you to get the idea here, so the idea is in your head. Because in the future, all I'm going to do is show you these little pulses. Right? So it helps if the idea is set. So just to make sure, I've got one more little thing that kind of let you look through this. Okay? So again, I copied that same picture over. Right? So right here, this is our spatial encoding, right, our GZ, and that is in tune with the RF kick. Right? That's what starts the whole beast. When that is done, I have to correct it when I come back out. I do my phase shift. It could be at different levels. That's going to set, you have to do that, I mean, it is right after, okay? Because you're trying to set how fast it's going to depolarize. That's your phase shift. And different heights front to back, right, are going to be dephasing at different speeds. That's going to set when do you read the dumb thing. And then I set my frequency encoding, my X direction, right at the time I'm reading that FID pulse. Because that's what's going to just tweak the difference. They're all going to be reading out right to left. This field will just slightly adjust them. So the ones on the right are at one frequency, left at a slightly different frequency. So good FFT will resolve them. Yeah.
My only thing was I thought, I just don't understand how the phase encoding determines anterior and posterior, because I thought that I was under the impression that phase was material specific and not spatially specific.
So I'm changing that.
Okay.
by imposing a magnetic field.
Okay.
And I'm imposing the magnetic field front to back, the Y gradient coils.
Okay.
The intensity of the B field, right, which is now being changed by that gradient, right? This gives me my B1, right? B0 is the base one, B1 with its things give you the gradient. By changing the gradient, if you look at the term for, how it dephases, it involves the material components, but it also involves the B field, right? So the larger the B field, the faster it's going to dephase. So by shifting your B field by the gradient coil front to back, I have now adjusted your, the dephasing speed. And it is linear with the B field. So it's a fairly nice, simple one to do. Does that all make sense?
Yes, I think the Y is starting to make more sense, which is good.
Yeah.
I have one question about on the initial Z gradient.
Yeah.
You mentioned we need to go backward to correct for when we put forward, but I don't really understand why we would need to do it in reverse if we were going to take it away.
So you turn it on, right? There's always going to be a little bit of edge effects that come when you turn something off. That's what you're trying to correct.
Okay, great. Makes sense.
Right. And we just draw it simply, but when you turn on, turn off, we don't worry about the turn on one because you're not doing anything.
Right.
So nobody's reading it. But when I turn it off, things are oscillating and I don't want to screw with that. So I just have to turn it off in a way that minimizes the effects on the signal. And that's all that's trying to show. And sometimes people don't even show it. Right? But I like the ones that do. It's misleading and it makes it look like it's perfectly symmetric and it's not. Right? But the idea is you're trying to handle the effects of, in this case, turn off's the only one that has things spinning. So therefore it's the only one you're going to get encoding problems from. Right? This is just trying to show you the effect of the spatial encoding, right? There at different frequencies. So therefore, whichever one you hit harmonically that's closest to it is going to resonate. That's just a pictorial form of whatever we said before. Anyway, that's most of this I think is fairly straightforward if it makes sense. That one was just to show you that, hey, I've got the constant thing, but I've got gradient theory that stimulates different parts. All right, if that makes sense.
Pretty clever.
Yeah, it's darn. I mean, if you think about it, people have done some really darn smart things. And the neat thing is that you can kind of build off these. So those initial areas all came basically from World War II. Right, the guy at MIT who was developing the basic radar stuff to detect planes, how do you correct for some of these areas to accurately find and locate enemies and everything? Actually turns out to have medical benefits, which is, you hate to say there's a benefit to war, but there is a benefit to war, right? I mean, you obviously don't want to do it for this reason, but it's incorrect to say that there's nothing that comes out of it. Anyway, so this does give one important area, right? So this is a simple pulse sequence that's coming on here, right? What really does matter is more the timing of this plus the correction to get to them is actually important. All right, so here you can see we're centering it with the RF pulse. All right, we do want it to be half that length. It's not necessarily perfect like that. You do get your GZ peaks off of those, right? And then on a basic one, this is if you're just looking for the FID decay. Right, and remember this is T2 and that's T2 star. That's the difference between the two lines. This one I think is fairly straightforward. While the FID, once you hit that peak, that's when you want to start doing the readout, analog to digital converter, the ADC. This is when you would do the X shifting. Right, we haven't done any phase or anything of that sort on this. But just to note that this is like the simple thing, right? Kick it and listen to the ring. While you're listening to the ring, that's when you would set the X. The book doesn't, they mention it in a couple things, but I'm just, since we've already kind of discussed some of it. All right, if that makes sense. Well, I'll talk about the coils because we need them, right? They've already come up a couple times here. So I've added some extra stuff. If you read the book, this is the book thing. I kept their thing in, but I added in some extra pieces of information because why show you all these different coil types, right? I mean, ooh, look, I can make a coil, right? So at some point you care, why do I care what these are? What do I use these dumb things for? These tend to be transmit coils. This is a receive coil, right? We often do dedicate them. You can bidirectional them. If you do, it's probably one of these, right? These ones really stink for transmission, but if you stick them right next to the body, they're not too bad. So you're only going to do a transmit receive if they're really close to the body. If you're out on the inside of it, it's going to be one of these because you're not trying to receive back on them because that's just going to be ugly. You can do some parallel array stuff if it's tighter bore. I guess I shouldn't say it never is. This is an older style, right? So this one's mentioned as a saddle coil. It might be hard to read. Think of these as the current direction. And they're trying to show you, so it comes in, up, out, back around, down, up, out, down, and it comes out, that's your output of the coil, right? So it's trying to, create, the field where you've got one side going one way, the other going the other, right? Similar to what the bird cage is doing there.
So for that coil number A, is that just the general shape of all the coils, or is that just the one coil?
That is that particular one, what's called a saddle coil.
Okay, right. So if we were to make an MRI with the saddle coil, would it just have the one ring around? In geometry, or would it have a couple of those?
This is for one particular direction.
Okay, I see.
Right? Now that's an old one, right? So that's a transverse electromagnetic. It's a very early, the saddle is a really early one. It's one of the first ones that was put in there. So essentially, pretty much nobody does that, right? It's a neat historic one. It's kind of cool to see how they initially came up with it because it is a pretty smart little design how they do it. The bird cage lets you get a little more control over it. This is another one. Again, both of these are, like I said, transmit coils. So we're, in general, call these volume coils. Volume coils, so there's three basic types. The volume coils like this tend to be ones that go over large volumes, whole body areas, and that tends to be on the inside of the bore of your MRI machine. Right, so these are typical style things that you would have on the inside of those. Anyway, that's kind of those, and they're really good for transmit. They really suck for receive. So I would not want to use one of those as a receive coil. So typically you would have type C over there. Those are receiver coils that go on. They're called surface coils because again they're best against the surface of the patient. That's their primary area. I included, so the book only shows you those two types. I included this one also because these are basically arrays of these. But these coil arrays are actually the nicest way to do it. Right? And I'll show you some pictures later that show you some of the differences between the quality you can get with these multi-coil arrays. But if you think about it, each of those arrays can be assigned to different areas physically, which means you can really tune it quite nicely to where things are at. These are the basic overlap patterns that are in here. And then you can also have, each of these can be a loop coil, right? One of these FO8 coils. The only difference between these and these is, are these independent coils here, or do they have the butterfly cross between them? So that's kind of one. So the butterfly is like that over here. The D coil is like this, but again, it does that same crossover in between. And then there are combined coils where I put a loop coil over either a D or a butterfly to get a really strong signal readout. Right, so there are different degrees, and you can imagine each one of these being then stuck inside. The reds and the blues are showing I don't activate them all at the same time, because I don't want crosstalk. Right, where these are overlapping, I can get some signal problems. Right.
I have a question about the
Sure.
signal problems. Isn't all of our spatially differentiable information frequency encoded? So why do we care about?
Because inductance between the coils.
Oh, I see. Okay.
Yeah, one of the noise problems you're gonna have is you're gonna get, essentially it's crosstalk, right? You're gonna get mutual inductance between them, and that can be pretty significant. And the signals you're actually measuring now are tiny, right? So if there's any amount of crosstalk, so we're gonna do a lot on the circuit to try to avoid any amounts of crosstalk. But one of the things we can do is to actually just, do multiple copies and walk through different sections of them. So I have ones that aren't on, so any induction across them doesn't cause a problem. But yeah, no, it's not a problem in your body. Your body will have noise in itself, right? But that's gonna all be related to Brownian motion. Those kind of random fluctuations within your molecules are gonna cause some noise kickback. But this induction here is another whole level. And then I added in this one too from a different book that just went through and talked about what different the uses of them, where would you typically see such a thing, right? So like for instance, if I'm doing head neck braid, I could see a bird cage with surface coils and arrays, right? I could see dipole antennas, right? I could see local shim array coils that are used to adjust these, right? These are different ways I could do readout. And that work well on, a head or brain situation that's going. Typical number of channels, you see it's really high, relatively speaking, for the neck, brain, things of that sort. Again, because you're dealing with, neuroscience, everything's really tiny and they need very precise images. And then they have references that goes to the back. This one actually, I said it's a book. I believe that's actually from an article. I have a link to the article on a later slide that came from. So if you want to look it up, that is a free one that's available out there. So if you're interested for that, then you can look at what they are. You can. You don't need it for this class, but if you do get into it, it's kind of nice to know what are they used for, what type of coils are useful in different areas. We feel good with this? Awesome. Okay, so I personally love circuits. Don't tell Charlie that, because we have to joke each other. But essentially, so think about this, right? I've got a coil element. Imagine this is one of my signal coils. I add that a preamplifier or some type of op-amp setup that's in here. There's a few things I'm going to want to do to tune this to be able to read different areas very precisely. Again, this helps me to reject other areas that might have gotten some slight amount of excitation. I can also tune this to reduce some of the readout. The primary ones for doing your tuning are these two capacitors, because you're not really changing the coil itself. That's a fuse to prevent you from damaging something. If you forget to detune when you're doing the kick, right, so that you're actually reading out when the kick happens, you will blow that stupid coil, because these are designed for your body's resonance back, right? So the rough equivalent difference I can make is, anybody ever see those little garden things that, have little phosphorus bits on them, and they soak up light during the day and then they glow for a couple hours at night? That's kind of your difference here between the one doing the kick is like the sun, and that little phosphorus thing is like your body responding back. Just to give you kind of like a brightness differential between them. So imagine, right, if I'm looking at the phosphorus thing at night, it's pretty, and I go, oh, that's lovely, right? If I stare right at the sun, I got a problem. So the fuse is there to prevent me from the I got a problem, right? There's a couple other things that are in there, but I can use these C tunes. This one is kind of fixed to provide a baseline to get me in the general area, and then I can just adjust this one, right, electronically, right, because we can have tunable capacitors for them, and that's what we do. So you can tune this one to pick up, and will, to pick up a particular spatial region better. Again, I want this coil to be resonant with the area that's spinning. All right, so just like the kick had to be resonant to cause it, this one needs to be resonant to get a good readout. So that's primarily done here, right? Then I have an inductor and this matching one because this is at 50 ohms and this ain't. Right, so I have to adjust between my coil and my amplifier's input to be able to get a good matching so I don't have a problem with signal reflectance and all kinds of fun stuff like that. Right? The remaining two ones here are what are called the detuning circuits. And these are here basically to prevent the accidental pickup of that initial powerful kick. Right? So you can think of this passive detuning one as having those sunglasses that change. Right? That's essentially what this one is doing. Right? It's got that capacitor with these two, right? So theoretically, it should let you go either direction you want to, right? But if you get a really big, powerful pulse coming in, it's going to charge this up, change the capacitance, detune the whole thing, and you're screwed. Which means you're not screwed, right? So it'll kill that signal on them. So that's the kind of whole trick. This is gonna, there's a finite time differential for other ones. So only if I've got a really big, powerful one is it gonna create that type of change.
So is the fuse just in case the detuning circuits don't work?
Or it's just too big even with that, right? The detuning, right? I detune the thing, it's passive, there's still gonna be that initial pulse. What if that initial pulse was huge? Right? I could still have a problem. These devices are really expensive and downtime is even more expensive, right? So you don't want a downtime. It's much cheaper to replace a fuse than to have your whole system torn apart and rebuilt. So yeah, it's just the cheap versus expensive thing. But this is designed to reduce it. You have to really try. This is what you're supposed to do. Essentially, you set a DC bias, you turn that on, you bias this individual diode here so that it's just on. You're bypassing that bad boy and introducing this different inductance. So now you've got a different path that's going through there, and in essence, you now go through an alternate routing and get a different inductance means it detunes by that amount. Does that make sense? So that's the whole trick to that DC bias one. The DC bias just biases this pin diode, right? Just giving you an alternate route. Otherwise, it's not enough to bias it and it's done. Okay, good. All right, so what you see on the other side is the two different ways you can set them up, right? This is the more preferred way, just because you can get a more tuned receiver and transmitter. But you can do them together for simplicity and it has less coils and whatever. But it's basically, you've got, the receive coil comes in, there's an RX switch. In essence, that RX switch would also drive your detuning. And you let it, so you do want a separate disconnect though, because you don't want it to go through your preamplifier or create a huge spike even with the thing detuned. So you want to switch so it's off because you don't want that going through the amplifier and just propagating down the line a gigantic, ever increasing wave of destruction. So anyway, that's, you've got a preamp and then the receiver and then a mixer that's coming from everybody else, and then the analog to digital converter, which does your readout going to the controller. Reverse, right, a DAC into your pulse generator. This is typically an op-amp type of a circuit to generate and create a bigger pulse. You don't want to accidentally turn that on and have a feedback around through to it, so you have to have a transmitter switch to prevent any small amounts of bias going through that heavy amplifier. And you can combine that here by switching which one does it go to, or neither. You do need the neither as an option because you don't want it pulsing accidentally or receiving and getting damaged accidentally. But that's basically the area. It's obviously analog all the way up to here. You feel good? Yay. All right. I'm presuming most people have had some electronic stores, so you feel comfortable with multi-stage amplifiers. All right. And that's really important because you're going to have different frequencies. The signals are weak. So you really need something that's almost a follower at first, right? Just to get you a strong signal, maybe a small amount of amplification. But then you move into the later stages. All right. So some things on quality of images. We need to go a little faster here. All right, this is our image quality triangle. This is your trade-off. Right? Choose what you want. Do you want the scan fast versus being willing to accept a slow scan? You want a good or bad signal to noise ratio? How much spatial resolution do you want? The more spatial resolution you want, the worse you're going to have to take one of the other two. You just can't have everything. Right? So it's trade-off, and that's what that's trying to tell you. You can't have all of them, and those are the three things we care about. Right, signal to noise ratio will obviously cause graininess. Spatial resolution, how big are your blocks, how thick are your slices, things of that sort. Right, scan time, if you allow me to do slower scans, i.e. I can do more repeats, and sometimes even the length of the response can actually enhance the quality of things, but you're going to spend time to get that better image. What does it matter? Right? SNR is a typical one. I found this really nice kind of chart of what affects it. So I always like graphical things. They always seem more memorable. Some of them, temperature-wise, right, should be somewhat obvious. Noise is going to be affected pretty strongly by temperature. Your signal does not really get a benefit from that. So particularly since a big chunk of your noise is Brownian motion in the body, there's also coil-related ones. And preamplifiers, they warm up. You're going to get more noise from that as well. The preamplifier noise, this is something when you look at your circuit is going to amplify certain things. That's something you want, particularly with your system. You're going to pick some up, right? Coil quality factor, right? Not all coils are created equal, right? Some of them have to do with the shape, some of the manufacturers, some of the material. There's a lot of different ones that go into this. There are all kinds of internal losses that happen, things of that sort. So, when you get down here, the geometry, the filling factor volume, what are you asking it to do, right? So, like it mentions the fact you're trying to get this homogeneous field over the entire volume, right? That's obviously if you gave me fancier, better coils, I can do a better job with it. More expense though, all kinds of other problems. These are just trade-offs in life, right? Same thing with receiver arrays. I want them packed tightly to be able to get a filling factor better, right? Because the tighter they are, the closer I'm getting my peak resonance readouts to be able to get, better resolution to it. So tightly packing is awesome, but that means crosstalk's going to be huger too. So to improve my spatial resolution, I've got to worsen my signal to noise ratio because that overlap is going to create more noise between them. Even if it's off, that coil is still going to read some, and then I'm going to get some back from it. So there's always a little bit of back EMF created between that coupling. So that's all there, right? And then the overall field strength. Right, so this is why people keep cranking up the magnetic field strength of these, because the better my field strength, the better signal to noise ratio I'm going to get. So that's why we want to go, people keep cranking up that field strength. That's what they're trying to improve, right? That's about the only unilateral improvement you can make, right? I crank that field strength up. It's going to make that, really hot, but I've submerged it in liquid helium, so life's good anyway, right? So it's just, that's a cost thing, but it is a direct, I get a benefit to this and I don't cause problems to the others. That's just a money interference one.
Okay, you kind of answered that, but besides cost and maybe blowing up the lab, is a bigger field strength just better?
So it's better for the resolution. There are questions about when you get really strong field strengths, what does it do to the human body?
Okay.
Right, because you're causing molecules to move.
Right.
This is essentially what a microwave does, right? So as I keep increasing that, this is why when I made the statement, yeah, it's completely safe, but then I said not everything, no matter what it is, there's no such thing as completely safe. But as far as completely safe goes, this is it. When you get too high, I get too much power I'm pumping into you, I start cooking you. Okay. So there is a little bit of a trade-off on these type of things. Yeah. Usually we do a lot of safe testing. It'll go through, we put them on animal standards long before, and it's not that we actually do, there are times when animal testing is done. This is not really an animal testing situation. We allow the vets to have a higher field first, so that, people doing a veterinary work get a better quality image earlier, but then we can also make sure it doesn't hurt longer term. And this is kind of part of the statement, but the canary in the coal mine, if you're familiar, miners would take canaries in because their smaller bodies would get killed off first. Well, the smaller bodies of animals can't handle the heat. So they'll be much more sensitive than you will. The link on the bottom here is the article that has most of this stuff in it that I've been mentioning. That is free. So let me just this is just kind of some images. You can see between 1.5 and 3 Tesla, right? I can get a better resolution, right? And I can scan a little bit faster, keeping about the same signal to noise ratio. And you can see the resolution is definitely better inside of it. I can trade that off to what do you get out of it. But, this is kind of a base one. Usually we increase that field, and that allows us to get more spatial resolution. Those 3 you trade off again. So this is with the arrays I was mentioning. So it's probably a little bit hard to tell because limits to projectors. But this is essentially take a look at an E with a 2-channel versus a 16-channel. And if you can see some of the resolution in here, it's just much better resolution that's inside of here. And it is faster. And I can actually, all of these things have improved, right? Because again, I just gave you a better readout machine. I gave you 8 times as many channels. So you just have more coils to do a readout. Remember, I kind of tie them in. So, yeah.
Dr. Schubert,
Yeah.
if you have more channels in your receive coils, is there any other cost besides just the upfront manufacturing cost?
So typically, if they're of a good enough quality that you can, get a readout in a decent time, so I don't have to do a whole bunch of repeats, you shouldn't. If they overlap too much, you could actually get some time delays that starts creeping into it. Yeah. All right. This is just, remember I mentioned you don't necessarily have to do flips as strong, right? How strong you flip. Now you'll see here I've got the TR, that's the time till you do your next pulse to measure it again. And TE is the echo time on there. So you can see I keep those the same. But if I've got a bigger flip angle, that's how hard I kick the thing, right? A stronger flip angle, a bigger RF pulse kick is going to give you a better signal. Therefore, your signal to noise ratio is going to be higher. All right, so that's kind of your initial amplitude of that kick is proportional to the flip angle. That's all that's trying to tell you. This one is when we're doing the recovery. Remember when we're trying to look at like T1 time, right? We had to give it a kick, waited a bit, we gave it the 180 pulse, and then we did the readout. And that was our echo time. And then we had a recovery period before we could do it again because you had to let things dampen off. So it turns out that if I set this TR, right, I can do it, right? This is 15, so I could set this at 200, but I won't get as high of a tissue contrast if I set it to 500. This is near ideal for the timing of it, for that signal to damp away. If you wait too long, you actually start getting worse contrast again.
Why would that be?
Okay, so part of this has to do with, there's like a peak that's on these. And the TR on this, right, is not just when the next pulse happens, but it's when I can do my flip inverts and all the rest of it for the T1s. Right, so when you're looking at that distance, right, how far out it can spread when I do the measurement. Because remember, there's actually, this doesn't actually correctly fully show the thing. There's the kick and the pulse. That's technically measuring T2, right? For measuring T1, there is initial kick to excite it, then you let it decay, then you give it another kick, and then you do. So there's two of these 90s and then a 180, right? There's a time between those, right? So, you know, 90, 90, 180, there's space between the readout then, right? And it's from the second 90 that you read this. So this TR would have to be dragged over here, and there'd have to be an initial excitation, right? So if you set it small, you're basically cramping this, and it hasn't had time for the other ones to decay, so you get low resolution. If you wait too long, it's decayed too much to get a readout. Because this TR time has to do with when the readout happens also.
Oh, okay. I didn't know that.
For when you're doing the T1, the 90, wait, 90, wait, 180 readout, that's proportional to TR. So if you give it too much time, then you're reading the TR later on. That's the only reason you would wait. Otherwise, you're waiting for nothing. Right? So there has to be there's a fixed distance over here between these. So if you make this longer, you're dragging this over. So the signal has gone down. All right, and that's why I just include the graphs below, just to remind you of those differing time pulses. All right, we might have to do some of this next time, because there's a bunch of ones here that goes. But I think this is a good discussion. So here's another one. This is just dealing with the echo time when you go on. All right, so if I cut the echo time, that goes on. Right, so I'm keeping my recovery time the same just for comparison. Right, you know, when you cut it, you cut your contrast, but you improve your signal to noise ratio. Now, here's why that works. The signal to noise ratio is because the longer you wait till the echo happens, the more the signal has died off. Because remember, in the background, your energy is decaying. So the earlier you measure it, you have a stronger signal. But the earlier you measure it, the less it's depolarized. So you're also getting crud around you that's also showing it, because those ones haven't died off. So if you read it earlier, your signal is stronger, but so is everybody else around you, right? So that's why the signal to noise ratio gets worse, because the signal is dropping, but your tissue contrast increases because everybody else dropped faster than you, right? So yay, wait longer, you know, you have no competition for the readout, but your signal is so low it's hard to read. Do it early, lots of competition, so it looks blurred, but your signal is strong. What do you want? Right? Yeah, I mean, it's just, you just understand it's a trade-off. In general, we tend to go here, right? And if you don't like that, if that signal to noise ratio isn't good enough, then you will deliberately start to scale it backwards. But we usually consider the spatial one as the important one. Okay, we are actually at our time. So I'm going to stop here. We'll pick up on the next one after. I think the next one after starts getting into, oh no, we have one more. You want me to grab me a couple minutes, or do people have the iPads? Okay, so we'll pick up on this one, talk about how do you get this is kind of fun because it's T1 and T2 and PD and all that, how do you get the different ones. All right, so we will stop here, and that's where we'll pick up next time. Have a lovely day, all.
Are we here Thursday?
Yes, here Thursday.
You'll let us know if we need to be.
Yeah. Well, I had other stuff I had to do Thursday anyway, because I just want to talk about recon and stuff like that. It's not really great. So I'm hoping next week, I'm trying to set that up with Jeff, but I haven't heard back yet, so.